All right, so this is the chemistry unit 5/6 study guide. So I know it says unit 5, but this is 5 and 6. So we're going to go over both things. So let's kind of get started. This shouldn't take very long. Okay, so the monatomic cation, that's our first thing. So if you want to understand what that means, okay, we got to break down the word. Mono or mono means one, okay, or singular. So this basically means one atom or one element, okay, that is a cation. Remember, cations are positive. That's a positive ion. So it is a single atom or element with a positive charge. Okay, now the reason why it is positive is because it is losing electrons. So when you are losing electrons, which are negative, it's going to make you more positive. So an example of that would be something like sodium, like Na with a +1, or like calcium with a +2. That is a monatomic cation because you have one element, okay, and it has a positive charge. Okay, moving on to next, we have monatomic anion. So again, that is one element, and an anion is negative. The way I remember these is cation has a T in the middle, so it looks like a plus sign, and then anion has two N's in it, so it makes it sound like more of a negative. Okay, so this is going to be a single atom or element with a negative charge. Okay, and its reason why it's negative is because it is gaining electrons. So if you are gaining electrons, you are gaining stuff that is more negative. Okay, you're gaining negative particles, so that's going to make you more negative. Okay, an example would be something like fluorine with a -1 charge, oxygen with a -2, okay, anything with a negative charge. Now, polyatomic, poly means many. So you've got multiple atoms that are going on or multiple elements going on. An ion just means something with a charge. So in this case, it is an ion consisting of two or more atoms or elements. Okay, example of that would be like that list we give you, like phosphate, nitrate. So like phosphate would be like PO4 with a -3 charge. Nitrate would be like NO3 with a -1 charge. So that is a polyatomic because if you look at PO4, I've got phosphorus and oxygen going on. So I have multiple or many atoms or elements going on. So that is what a polyatomic is. A monatomic is just an element by itself. Polyatomic means there's multiple elements going on in one compound. Okay, oxidation number, that is simply the charge of an ion. So by a charge, we mean something like -1, +2. Okay, that's what an oxidation number is. It's just a fancy word for charge. Now, a transition metal. Okay, I'm going to go down here to the periodic table to kind of show you where the transition metals are because I get a lot of confusion on that. So if you look at your periodic table, your transition metals are going to start in this group right here, so 3B, and it's going to go all the way to the staircase. Okay, it does not stop at the 2B here. Okay, it goes all the way to the staircase. Now, the only ones that are not considered transition metals because they have the same charge the entire time is silver, which is going to be a +1, zinc is always a +2, and aluminum is a +3. Okay, so anything besides those three from this 3B group right here, all the way to the staircase and under the staircase is a transition metal. Okay, so that means we do not know what the charge is. It could be anything. Transition means it can change. Okay, so that's when we start using Roman numerals, and which we'll get to in just a little bit. We'll do more practice on that. But I want to make sure everybody knows visually where those transition metals are. So let's go back up to the top. Okay, so a transition metal is a metal that can have more than one charge. Okay, now we usually use Roman numerals to indicate that, so Roman numerals are involved to tell us the charge. So please be careful with that. It tells us the charge. It does not tell us how many there are, it just tells us the charge of one. So if I had something like this, like Fe with a +3, that's iron, with a +3 charge. If I were to write out the name, I would write iron and then 3. Okay, so in case you need a recap on your Roman numerals, here is your Roman numerals. 1 is just I, 2 is II, 3 is III, 4 is IV, okay, 5 is V, 6 is VI, and 7 is VII. 7 is as high as you'll go. Now, the most confusion happens on 4 and 6. Okay, the way I remember this is you have 1 before 5. Okay, what is 1 before 5? That would be 4. Or the way I remember this is the I comes before the V, so before meaning 4. Okay, and then VI, you have I coming after the 5. So what is 1 after 5? That would be 6. Okay, so that's a recap on your Roman numerals. Okay, so let's move on next. Describe properties of an ionic compound. So an ionic compound, so you need to make sure you know what that is. That is between a metal, which is the left side of the staircase, and a nonmetal, which is the right side of the staircase. That is between a positive and a negative. Okay, it's one of the strongest bonds out there is because you have the opposite charge. Now, characteristics of these is because it is so strong, it has a high melting point. So a high melting point and a high boiling point. Okay, so basically what that means is you need higher energy to break that bond apart. Okay, so it takes more heat to break that down. Okay, when it is a solid, it is very hard but brittle, meaning it can break. Okay, so when it is in solid form, it is a non-conductor. And what that means is it does not, you cannot transfer electricity through it. Okay, so it's a poor conductor, so a non-conductor. Okay, now they are dissolvable, so many are soluble. That just basically means that you can dissolve, so many are, you can dissolve them in water, so they're soluble in water. Next one is when they are dissolved. Okay, the ions float and conduct electricity. Okay, so when dissolved, the ions float and conduct electricity. So as a solid, they can't really conduct electricity, but when they're dissolved in water, okay, they can. Okay, and those are called electrolytes. Okay, next one, my last one is it forms a lattice structure. And what that is that's just a repeating crystal structure. So if you have like ions that are just next to each other, okay, basically what they're going to do is they're just going to line up in this repeating grid. So that is what like a lattice looks like, is just a repeating grid. Okay, which basically gives you a crystal structure. Okay, so those are your properties, so make sure you know those because we can ask questions on which of the following is not a property of an ionic compound. Okay, moving down here to this part, we're going to do our periodic table. So I'm going to go back down to my periodic table because I want to make sure everybody's on the same page before we start doing that. Okay, while we're doing this video, it will help to have your periodic table handy so you can look at it because I'm not going to be able to scroll down to this every single time. So I'll refer back to the periodic table. So let's go over this real quick. Let's do a brief catch up on your periodic table. Okay, so let's look at our charges. So remember the perfect number of valence electrons being your outer shell electrons would be 8. Okay, if you want to know how many valence electrons something has, look at the top. So if you look at C, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, those are your valence electrons. Okay, so remember 8 is the most you can have. Now this middle section right here, remember we talked about that as transition metals, so we don't know what they have. They could be anything. Okay, the other groups, okay, we do know. Okay, so remember, if you need a refresher, groups are the columns. Those go up and down. Okay, period is when you go left to right. Okay, so if I asked you something, let me clear this up. So if I asked you to locate something, I'd ask you to say, well, what element is in group 15/5A and period 4? Okay, so what you would do is you would find 15/5A, which is right here. Okay, so you would go down until you meet period 4. So if you look on the left of your periodic table, that 4 right there, that's your period. So you just figure out where do they meet. So go all the way across until you hit right here. Okay, so arsenic would be in group 15/5A and period 4. Okay, so it's kind of like Battleship. You're just seeing where they meet up. Now, also a refresher on your groups. Okay, so this first column right here, that is your alkali metals, okay, which are very reactive, more shiny. Okay, so you can kind of go back in your notes and look at that stuff. Okay, your alkali earth metals are that next column, so that's the way I remember that, is those alkali metals, and then alkaline earth metals would be next. Then you have your transition metals, which are going to start here and going to go all the way to the staircase. Okay, then you have your metalloids. Metalloids are basically anything that's touching that staircase. Okay, what that basically means is they kind of act like both metals and non-metals. Okay, so they're kind of in that limbo. Okay, so those are metalloids. Metalloids just touch that staircase because they're kind of in between. Okay, because on this left side of the staircase, so all this side right here, anything left of the staircase, that is going to be metals. Okay, so not everything you think is like a metal. Like sodium is actually a metal. So everybody kind of thinks metals have to be shiny, like you think of when you see like a car or pipes, things like that. That's not the case. Okay, now on the right side, these are your non-metals over here. Okay, on the right side of your periodic table, those are non-metals. So if you look, most of your periodic table is going to be metals. Okay, some of it will be non-metals, those are going to be on the right. The way I remember that is if you look on the left side, you got things like iron, titanium, those are definitely metals. If you look on the right side, you have things like oxygen, fluorine, helium, those are not metals. Okay, now the one exception is hydrogen is not a metal. Over here, it's a gas, but since it has one valence electron or a +1 charge, that is why it's over here on the left side. Okay, so hopefully that kind of cleared up some of your groups. Well, also I forgot some of them. You have your halogens, okay, which is at group 17/7A. So they are very active because they only need one more electron to make that perfect 8. And then you have your noble gases. So hopefully you kind of remember that from the last unit. Noble gases are on the right. They're not very reactive because they have their 8 electrons. So they don't need anything. They don't need anybody, so they're not going to bond. Okay, so that is a recap on your groups. So let me clear some of this up real quick. And then we'll talk about charges because that is what we're going to need here in just a second. So let me clear this up. Okay, so again, in order to know the charge, you need to know the valence electrons. So remember, the perfect number is 8. So over here on the right side, helium, my charge would be 0 because I have 8. I don't need anything, okay? Now this group 17/7A, if you look, I have 7 valence electrons, so I only need one more. So it's going to gain one more electron, which would give you a -1 charge. Now the way I look at that is if I have 8, I'm basically missing 1, so that's why it's a -1 charge. Then I have group 6A, that means I'm missing 2 or I'm going to gain 2, so that would be a -2. Then I have 5A, that would be a -3, okay, because I'm going to gain 3. Now this group right here, 4A, this can kind of go either way. So carbon and silicon can be positive or negative. So it just depends on who it's bonded with. Okay, so if carbon comes first in a compound, like something like, let's say CO, something like that, calcium or carbon can be positive, or it can be negative. If I do something like NaC, something like that, it can be negative. So that's kind of one of those kind of goofy ones. So we don't use that one a ton. But it can go either way. So it's a plus or -4 because it could give 4 electrons or it could gain 4 electrons. Then you have group 3A. Okay, so this is where you realize I have 3 valence electrons. So boron has 3 valence electrons. It's not going to gain 5. It doesn't have the ability to steal 5. So it's just going to give up its 3. So that's why it's a +3 charge. Then we're going to jump across this giant group to over here. So group 2A. I have 2 valence electrons. I'm not going to be able to steal 6, so I'm just going to give them up. So it's going to be a +2 charge. And then this group would be a +1 charge. So please make sure you have those charges down because if you do not, that's going to make this very difficult when it comes to bonding and balancing. Okay, now in your transition metal block, so please make sure in this middle section right here, so starting right here, going all to the staircase, we don't know what the charge is. It could be anything, so we'll go over that here in a second. But silver is always going to be a +1, zinc is going to be a +2, aluminum is going to be +3. So that is kind of a recap on your periodic table and your charges. So please make sure you have that kind of down. Go rewind it if you need to. Take whatever you need from that. So we're about to move on to the next part. So this will help if you have your periodic table handy. Okay, so please make sure if you need help or need practice on this, pause the video and then play it and see if you did it right. Okay, so that's something that can help you out. Okay, so if you look at this, cesium, if you look up cesium on the periodic table, the symbol would just be CS. That's the abbreviation. Okay, it is in group 1/1A, so it's in that very first column. So the valence electrons, if you look at that 1A group, that tells you it has 1. Now, oxidation number, that just means charge. So that would be a +1 in that group. Ion symbol just means that's the abbreviation with the charge. So CS with a +1. Ion name, okay, so remember when it is a cation, so I'm going to kind of do this kind of a little bit backwards. This is a cation because it's positive. We do not change the name of cations at all. So if it's cesium on the periodic table, its ion name would just be cesium. Okay, and which we'll talk about when do we change something here in a second. Okay, the next one is strontium. So SR is strontium. Okay, that is in that group 2/2A. So if you look at 2A, that means I have 2 valence electrons. My oxidation number would be a +2. My ion symbol would be a SR +2. My ion name would just be strontium, so we're not changing that cation at all. So that means this is a cation because it has a positive charge. So let's move on to this one. Now BR is bromine. That is in group 17/7A. So that means I have 7 valence electrons, which gives me a charge of -1. Okay, so please be careful with that. 7 valence electrons does not mean I have a charge of -7. It means I have a charge of -1 because I'm missing an electron, or I'm going to gain one. So my abbreviation or ion symbol would be Br with a -1. Now, since this is an anion, meaning a negative charge, we have to change it. We have to change it from bromine to bromide. Okay, so if I have something like this, like NaBr, my name would be sodium bromide. The way I remember that is because if you just said sodium bromine, it would sound like you were just picking 2 elements off the periodic table and just saying them randomly. When you tell me it's bromide, you're telling me this bromine is attached to sodium. Okay, so that's why we have to change the name. Okay, so let's look at another anion. So because we've done a couple of cations, so let's do the P. That would be phosphorus. My group for phosphorus would be 15/5A, which would give me 5 valence electrons, which would give me a -3 charge. Okay, because since you have 5 valence electrons, that means you need 3 electrons. So your ion symbol would be P, so the abbreviation, with a -3 charge. Now your ion name, remember this is an anion, so that means we had to change it from phosphorus to phosphide. Now if you need help remembering where do you put the "ide," the way I remember it, it should always be 2 syllables. So like something like nitrogen becomes nitride, bromine becomes bromide, phosphorus becomes phosphide. So there are multiple ways you can change that, so it should be just 2 syllables. Okay, so hopefully that kind of helped out there. I'm not going to go over all these because I don't want to take up time. So let's move down to the next one. So 4 would be, now this is Lewis dot structure, so we're going to do a little bit on this. So we're not going to do all, this will make more sense in this when we come up in January and stuff. So we kind of taught this a little bit, but this is basically a visual on how bonds occur. Okay, so if we looked at aluminum, aluminum is Al with a +3. Oxygen is O with a -2. So if I were to put those together in a formula, okay, I'm going to need 2 of these aluminums and 3 of these oxygens. So I can take a minute and explain that. The whole goal is when you write a compound, it has to be balanced. That means you have to have the same positive number as you do the negative number. So if you look at this, I have a +3 to -2. This is not balanced at all. So there's 2 ways you can do this. One would be the crisscross way, meaning you can take the 2 down here. That means you need 2 aluminums. And then you could take 3 down here, which means you need 3 oxygens. Okay, so that's one way you can do it. Another way you can do it is you can look at it mathematically. If I have a +3 and a -2, I would think, well, what is the closest number that can be divided by both 3 and 2? That would have to be a 6. So if I need aluminum to be a +6, and each one is a charge of +3, how many would I need? I would just need 2 of them. If I need oxygen to be a -6, and each one has a charge of -2, how many would I need to get to -6? I would need 3 of them. Okay, so that's basically when you do that crisscross method, you're getting them to the same number. So that means this aluminum has a +6, this oxygen has a -6. In order to write a compound, it does have to be balanced like this. You have to cancel out to 0. If it does not cancel out to 0, that means you did something wrong. So when we do Lewis dot structures, here's a little hint on Lewis dot structures is one thing you're going to do is I have 2 aluminums to draw. So I'm going to go ahead and draw 2 aluminums. Okay, each one is going to have 3 valence electrons. Okay, because it's in that group 13/3A. So the way you do this is each one has 3 dots. What you're going to do is you're going to start at the top with a dot, and you're just going to go clockwise. So 1, 2, 3. That's all it's got. I'm going to go down to this aluminum. This one's got 3. So 1, 2, 3. Okay, so there's my aluminum Lewis dot structures. Now I need 3 oxygens, so I'm going to draw 3 oxygens. Okay, each one of those is going to have 6 valence electrons because it's in group 6A. So I'm going to start at the top. So 1, 2, 3, 4, 5, 6. So once you get to that past 4, you can start doubling up. So each oxygen is going to have 6. So 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Now this is probably a more difficult one to start on. I will do a more easier one here in just a second. Okay, so if we look, oxygens have 6, they need 2 more. Okay, so what they're going to do is they're going to start taking electrons from these aluminums to basically equal out to 8 because they want that perfect 8. So 1's going to go here and fill up this vacancy right here. 1's going to go fill up this vacancy right here. So that oxygen is going to be good because now it has 8. Now we're going to move on to the next. This electron from aluminum is going to go here. This electron from aluminum is going to go here. So now this oxygen has 8. This electron's going to go to this oxygen here, and this electron's going to this oxygen here. So now that one has 8. So this is why 3 oxygens would need 2 aluminums. Okay, is because you have to have enough electrons where it's going to balance all those anions out to E where everyone has 8, so everyone's happy. Okay, so let's do a little more simple one, and then we'll move on. So calcium is a +2, chlorine is a -1. Okay, so if I were to write out a balanced formula, that 2 would go here, that 1 would go here. So that means I need 1 calcium and 2 chlorines, which should make sense. If I have a +2 charge and then chlorine is a -1, I would need 2 of those chlorines to balance out with that +2. So if I look at calcium, it has 2 valence electrons because it's in group 2A, so I'm going to do 2 dots. Now chlorines, I'm going to have 2 of them. Okay, and chlorine's in group 7A, so it's going to have 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that means chlorines are really close. All they need is 1 more, and then they're good. So since calcium has 2 to give, 1 chlorine wouldn't do me any good. I mean, this chlorine would be happy, but if you only had 1 chlorine there to balance it out, it wouldn't work because now calcium has this 1 that it's not using, and it wants to get rid of. So in order to get rid of it, it needs another chlorine to come pick it up. Okay, so that's what's going to happen is that calcium is going to give up its 2 electrons, and it's going to give 1 to this chlorine up here, and then it's going to give the next one to this chlorine here. So now everyone's happy. So both chlorines have achieved their 8, and now calcium has gotten rid of its 2. So that means calcium now has its last shell would basically just disappeared because it gave up those 2, and now it has a full shell as well. So this is more of just a visual on how these bonds are occurring. You're just basically giving electrons from the cation, okay, the cation's over here, and the anion's over here. You're just basically giving electrons from the cation to the anion. Okay, so now let's move on to kind of the next section. Okay, describe atomic radius and its trends down a group and across a period. So atomic radius, that is simply the size of an atom. Okay. Ionization energy, that is the energy to remove an electron. And electronegativity is the ability to steal an electron, or the likeliness to steal. So the way I'm going to describe these trends is on the key. I have those written down, but I'm going to kind of show you visually on the periodic table. So let's clear this up right here. All right, so atomic radius is going to be biggest down here, okay, at francium. Okay, so as you go down to the left, it gets bigger. So smallest will be up here towards helium. Biggest will be down here towards francium. So as you go across, let me clear this up. As you go across a period, oops. Let me fix that. Don't know what happened there. So as you go across a period, it actually gets smaller because what you're doing is you're adding more protons, which are going to pull those electrons in tighter. So I know most people are thinking, well, you're also adding electrons, but what you're doing is you're not really adding more energy levels, like you're not adding more rings like you would going down, is you're technically just adding more electrons to the current energy levels, okay, but you're also adding more protons. So your rings aren't really you're not getting more energy levels or rings, you're getting more protons, which will pull those electrons in tighter. Now, as you go down a group, it's definitely going to get bigger because you're adding more and more of those energy levels when they're getting further and further away from the nucleus. So down here towards francium, it's going to be the biggest because you're adding a ton of energy levels, and they're actually getting further away from the nucleus because those energy levels do not like each other. They're all made up of electrons, and so they're all negative, and so they're actually pushing each other further out, and they're shielding that nucleus from being able to pull. So as long as you pretty much know that atomic radius gets bigger as you go down to the left, that makes it the easiest. Okay, so now we're going to talk about ionization energy. That's the energy it takes to remove an electron. It's going to get a lot higher the opposite way. It's going to get higher as you go up towards the top. Now think about it, it's the energy it takes to remove an electron. So basically think about this, is francium, say francium is a parent, and they have 87 kids. Okay, that is a lot of kids to keep a hold of. Okay, so if something kind of came along and wanted to grab one, it would not take much because you're so focused on all these other kids and all these kids are so far away, it would not take very much energy to take one of those. Now, as you go up towards helium, okay, it's getting very small. Okay, you have these electrons getting pulled in tighter, and you have less and less of them. Okay, so if I have 87 kids, it wouldn't take very much to grab one. Okay, if I have 2 kids or 9 kids, it's going to be a lot harder, so it will take more energy to steal one of those from me. Okay, so it gets stronger as you go up, or it gets higher as you go up towards the right. Okay, so as you go across a period, it's going to get harder and harder because remember what I just talked about is those electrons are being pulled in tighter and tighter. So your radius is actually getting smaller. Now, if those electrons are getting pulled in tighter, it's going to take more energy to steal one of those electrons away. So as you go across a period, it gets harder, meaning the ionization energy gets higher. As you go down a group, it just gets easier and easier because you're adding more energy levels. Those electrons are getting further and further away. Okay, so it does not take very much. But as long as you basically follow this kind of pattern right here, as you go towards the top right, ionization energy gets higher. Now, the next one is electronegativity. That is the ability to steal an electron. That goes the same direction as ionization energy. As you go towards this top right, it gets stronger. Okay, because if you have less, like fluorine, fluorine has 7 valence electrons. How many does it need to be perfect? It needs 8. So it only needs 1 more. So that means fluorine will almost do anything to get 1 more. So it's going to have a higher ability to steal. Now, it's also because you have less electrons, like here down at francium. You have so many electrons in the way that are blocking that nucleus. That nucleus is not going to really be able to pull an electron from something else. Okay, so there's too much going on in the way that would block the pull of that nucleus. Versus fluorine. Fluorine's only got 7 valence electrons. There's not a whole lot blocking that nucleus from pulling something from another atom. Okay, so as you go cross to the right, okay, your electronegativity gets stronger. One, because the atom gets smaller, so that means that nucleus can basically pull from another atom. And two, the way I think of it is you're getting closer and closer to 8 valence electrons, so they're gonna want to steal more. Now this last column, the noble gases, they don't care. They have their 8, so when it comes to electronegativity, they have basically 0 electronegativity because they have their 8. They don't want an electron, okay? As you go down a group, it is going to be harder and harder to steal an electron. It's going to be very weak because it's got so much in the way, it's blocking it. Okay, so basically as long as you know, let me clear this up real quick, is that atomic radius gets bigger towards the bottom left and electronegativity gets bigger and ionization area gets bigger as you go towards the top right. Okay, so let's go back up here and look at our rankings. So this one, I want to rank from smallest to largest atomic radius. So smallest to largest, so please be careful. Look for underlined and bolded things on the test because that can easily mess you up. So I'm gonna go down here and I'm gonna circle what we have. Let me go to my periodic table. So I have francium, which is right here. Oops, let me go back to my pen. Francium right here. I have phosphorus right here. I have nickel, which is right here. And I have barium right here. And I want to rank it from smallest to largest atomic radius. So that means it has to go, smallest would be up here towards fluorine and helium, and it would go this way. So if I want to rank it from smallest to largest, my smallest would be phosphorus. Then it would be nickel, because nickel's next, and then it would be barium, and then it would be francium. Okay, looking at the next problem, so if you have your paper next to you, okay, my next problem, I'll go ahead and write it down here so I'm not scrolling so much. Okay, my option is silicone, aluminum, oops, I have no idea what's going on. Let me figure this out. All right, I think I'm good now. All right, so I have silicone, I have aluminum, I have chlorine, and I have magnesium. Okay, so let me clear this up real quick. So silicone's right here, aluminum's right here, chlorine's right here, and magnesium's right here. So even though they're on the same period, it's actually going to get bigger. Remember, you're trying to get bigger towards this way. So it's going to get bigger as you go to the left, okay? Because those electrons are not being pulled in as tight because there's less protons. So the smallest would be chlorine, then it would be silicone, then it would be aluminum, and then it would be magnesium. So magnesium would be the biggest, okay? Chlorine would be the smallest. Okay, the next columns or the next section, so again, I'm not going to scroll up too much on that because I'd like to save some time. Okay, you can look at yours or you can pause it. My next option is I want to rank from smallest to largest ionization energy. So that means smallest would be down here, biggest would be up here. Okay, so let's go ahead and take a look at our example. Our example would be cesium, potassium, rubidium, and lithium. So I'm going to circle those. So cesium will be right here, potassium will be right here, rubidium will be right here, and lithium will be up here. So even though we're not going towards fluorine over here, okay, as you go up, there are less and less electrons in the way, which basically means it's going to be harder and harder to steal one of those electrons from the nucleus. Okay, so it's going to get stronger as you go up. So that means cesium would not take very much energy. That would be my lowest. Then it would be rubidium, then it would be potassium, and then it would be lithium. Okay, now let's move on to the next example. I have Ag, I have O, I have MO, and then I have F. Okay, so Ag is right here, that's silver. Then you have oxygen. Let me clear up that fluorine right there because we're not using that. Okay, well, actually we are. And then we have MO, which is right here. Okay, so remember, it's going to get stronger as you go this way. So that means MO would be the lowest, then it would be AG, then it would be O, and then it would be F. Okay, so F would be, it would take a lot more energy to steal from F. All right, so the next part is we're going to rank from smallest to largest electronegativity. Okay, so that's the ability to steal. Okay, so that's going to get bigger towards the top right-hand corner like we just did. So my example would be FE would be the first one, and then TI, and then BR, and then GE. Okay, so FE is going to be right here. TI is going to be right here. Bromine is over here. And then GE is right here. So again, this is the ability to steal. So as you go towards the right, those electrons are going to get tighter, which means that protons have more of a pull, so they have a better ability to steal. So the lowest electronegativity would be titanium, then it would be iron, then it would be germanium, and then it would be bromine. So bromine would be the highest. Okay, last example, and then we're moving on to the naming stuff, I believe. Okay, so the next one I have sulfur, indium, gold, and silver. Okay, so sulfur is right here, indium's right here, gold's down here, and silver's right there. So as you go towards the top right, it's going to get stronger. So that means gold, or it's going to want to steal more. Gold will be the weakest and won't be able to steal. Silver will be the next one. Then it would be indium, and then it would be sulfur would be the highest. Okay, so hopefully that kind of helped out there. So we'll move on to the next section. Okay, so that'll actually bring us into the main part of this test. The bulk of this test and the quiz you took is from cations, anions, chemical formula, and chemical name. Now, I'm not going to do all of these, but I'll do a good amount so that we feel we're kind of comfortable. So you will need your periodic table handy on this because I can't scroll back and forth. It would just take too much time. So cation, remember that is your positive charge. So your cation needs to be the abbreviation and the positive charge. So please do not forget those. Anion would be your negative one. So it's the abbreviation with the negative charge. So again, remember your charges, you have to know those. So going back down here, you have to know this +1 right here, this +2, +3, plus or minus 4, -3, -2, -1, 0. If you don't have those down, it's going to be very difficult to even know where to start. Okay, you also need to make sure you know that silver is a +1, zinc is a +2, aluminum is a +3. Okay, now we will come down here and every now and then to look at the periodic table, especially to help out with transition metals. Okay, but I'm not going to refer to it very often, so just make sure you have yours handy. So let's look at this first one. We have titanium, which is a +5. Nitrogen is a -3. That is not balanced out. Okay, so that means what I'm going to do, you can do the crisscross. You can take the 5 here, and you can take the 3 here. That means I need 3 titaniums, and I need 5 nitrogens in order to be balanced out. Now, if you notice, this is an error I have been seeing, is please do not take a -3 here and a +5 here. You cannot have -3 titaniums. Okay, so do not take the charges, just take the numbers, because these subscripts down here just tell you how many you need. It does not tell you if it's positive or negative. That's what the charges are for up top. Okay, so please do not take the signs with it. Okay, now when we write our name, okay, our cation, remember your cation, you do not do anything to it. You just tell me what it is. That is titanium. Now, this is where you got to be careful. So look at your periodic table. Titanium is right here. That means that is a transition metal. Transition metals have to have a Roman numeral. Now, I will highlight the things you do not need a Roman numeral for. You do not need it for this group right here because it's always +1 and +2, the +1. You do not need it for right here. Okay, that is always +2. You do not need it for this silver. That is always a +1. You do not need it for this zinc. That is always +3. And you do not need it for aluminum. Zinc is +2. Aluminum is always +3. I will highlight what you do need a Roman numeral for. I can use a different color. Is you basically need everything from this 3B all the way to the staircase. These are transition metals. So basically anything I've highlighted in orange, you need a Roman numeral for. You do not need a Roman numeral for your nonmetals. Remember your nonmetals, I'll do this in blue, Your nonmetals are over here. You do not need a Roman numeral for those. Those are negatives. Okay, you only use a Roman numeral for cations. Okay, so please make sure you are using it for just the orange that I've highlighted. So let's go back up here. So remember your Roman numerals. So remember, it is for your charge, not how many you have. It's just for the charge of 1. So its charge is 5. So that would be V. So titanium 5. And then nitrogen becomes nitride. So please remember, if it is just an element by itself off the periodic table, so nitrogen is on the periodic table, you have to change it to nitride. Okay. The next one is CaNO3 Okay, so calcium is on your periodic table. It's in group 2, so we know that's a Ca plus 2. That is always going to be plus 2. Nitrate is on this polyatomic list right here. Okay, so here is one hint when you are doing something on this test. If you are searching all over your periodic table for something and you cannot find it, please check this polyatomic group first, because if you're looking for something like cyanide, you're not going to find it on the periodic table. So I like to tell my students is it will save you so much time if you check this list first, and then if it's not on here, that means it has to be on the periodic table. Okay, so it's a lot easier and it will save you time. Now, this list is your polyatomics. Okay, so you have things like nitrate, which is NO3 with a -1, which is what we're dealing with. You cannot alter any of these. Okay, you cannot change, let me highlight this, you cannot change any of this. Okay, you cannot change ClO3 at all. It always will be ClO3. Chlorate will always be ClO3. Okay, you can use the charge to balance, but you can't change the charge either. Okay, so please make sure you're referring to the list and do not edit anything. So we'll do plenty of examples where I'll show that. So NO3 is nitrate. So I got that from down here. So let's go back up here. So NO3 with a -1. That is your anion. Okay, so it should make sense. If you look at your chemical formula, I have 2 of these nitrates to balance out with 1 calcium, because if you look, calcium is a +2. So if I took this 2 here and took this 1 from nitrate here, okay, that means I need 1 calcium and 2 nitrates. But if you noticed, if you need more of a polyatomic, you have to put it in parentheses. Okay, you have to keep nitrate as NO3. You cannot edit the 3. All you can do is put in parentheses and then put how much you need outside. 1, because it would look stupid. It would look like this. If you did not have it, it would have NO32. Okay, so please do not tell me I need 32 oxygens. Okay, that is a big difference. Okay, so let me clear that up. Oops. Now, when it comes to my name, Ca is calcium. You would see, is calcium a transition metal? Nope, it's in group 2, so I do not need a Roman numeral. And NO3 is nitrate. Okay, so if you notice, up here you have nitride. Down here you have nitrate. Anytime you see IDE, that means it came from the periodic table. Okay, it is just an element by itself. So nitrogen is just by itself. Anytime you see something like this, so going back to your periodic table, or going back to your group down here, anytime you see 8s and ites, those are always going to be down here. Okay, that is on your polyatomic list. So please, I see that error all the time. Is ides is when you're using the periodic table. So basically anything in blue, you're going to use ide. Anything that has 8 and ite will be on this list right here. Okay, let's go back up. Let's look at the next one. We have nickel 2 carbonate. So this 2 right here, that means nickel is a transition metal. This 2 is telling me the charge of nickel. So I'm telling you what it is. So that means nickel is Ni with a +2. It doesn't tell me I have 2 of them. I could have 2 of them, but it's not telling me how many I have. Okay, carbonate is on that polyatomic list. That is CO3 with a -2. So I would see, are those balanced? They are. Okay, so if they are already balanced, you do not need to crisscross. You can if you want to, but that's where you usually lead to errors because you would need to reduce. So let's just say I did crisscross, and I did Ni2 and CO3 2. Do I need 2 here and 2 here? No, because I can just reduce those. I could simplify it. I wouldn't even need those 2s at all. Okay, so the way I tell my class is if the numbers are already the same, just put them together. You don't even need to crisscross. So that means all I got to do is just put nickel with carbonate. Now, could you put a parentheses around this CO3? I mean, go for it. You do not have to. I usually only do it if I need more. Okay, but you're not going to be wrong either way. Okay, the next one, I have AlOH3, so aluminum. So Al is aluminum. If you look on your periodic table, that is a +3 charge. And then OH is actually on your polyatomic list. That is hydroxide. That is OH with a -1, which should make sense. If aluminum is a +3 and OH is a -1, that is why I have 3 of them to balance out with that aluminum. But if you notice, OH is in parentheses. You cannot put that 3 right next to the H. You need to put in parentheses first and then put a 3. Now for the name, Al is just aluminum, so you don't need to do anything there. Now, if you look at your periodic table, aluminum is in the transition metal block, but if you look, these 3 are always the same. You do not need a Roman numeral for those 3. Okay, so you can just tell me aluminum. You do not need a Roman numeral. And then OH becomes hydroxide. Next one, I have Sr plus 2 HCO3 with a minus sign. Anytime you see a minus sign, that is imaginary 1. Okay, so I can see those are not balanced. So if you want to do, you can do crisscross. You can take that 2 here. You can take that 1 here, meaning I need 1 strontium, but I need 2 of these HCO3. So make sure you put it in parentheses first. So HCO3 goes in parentheses, and then put a 2. And there you go. It's balanced. Now your name would just be strontium. Oops. And HCO3 is on your polyatomic list. That is bicarbonate. So strontium is not a transition metal, so I do not need a Roman numeral. So you're good there. Next one, I have H plus, so that's basically a +1. Oops. And I have PO3 with a -3, so I can see those are definitely not balanced. So I can take this 3 here, take this 1 here. So I need 3 hydrogens and only 1 phosphate. I'm sorry, PO3. That is not phosphate, so please watch out for that because I'm about to explain it. So do I need to put PO3 in parentheses? You do not. Can you? You can if you want to, but I don't need any more, so I'm not going to put parentheses. Now, if you go down to the list, please be careful on this. Please check. PO3, that is phosphite. Oh, here we go again. Here we go. That is phosphite. Okay, PO4 is phosphate. So since we give you this list, please don't make simple mistakes like this. Just check this. PO3 is phosphite. So all I got to do is come up here and just put hydrogen, phosphite. Oops. Helps if I could spell and write. Phosphite. Okay, and that's your answer. Now, moving on to the next, you have NH4,2SO4. This just looks like a mess. Okay, but this is actually just 2 polyatomics. So if you looked at your polyatomic list, NH4 is actually ammonium. That is the only one on that list that is a cation. SO4 is also on that list. So instead of you trying to break down and find what everything is, it's just simply 2 things put together. Okay, so you have NH4 the +1, SO4 the -2. So it should make sense that you need 2 of these NH4s to balance out with 1 SO4. Now, NH4 is called ammonium. It is on that list. And SO4 is sulfate. Okay. Next one, I have MgO. So Mg is magnesium. That is Mg with a +2. It's in that group 2. Oxygen is O with a -2. Okay, I'm getting both of those just from the periodic table. When it comes to the name, Mg is magnesium. Is magnesium a transition metal? No, it is not. It is not in that part that I colored, so I do not need a Roman numeral. And oxygen just becomes oxide. It doesn't become oxate. It does not become oxite. Okay, it is just oxide. Anytime the anion just comes straight from the periodic table, just end it in IDE. Now, the next one, AlC2H3O2 with a 3. This looks like a pain in the butt too, but it's not too bad because you have aluminum, which is always a +3. And that big compound there is just acetate. That is just C2H3O2 with a -1. So it should make sense. That's why I have 3 of them, is because if each one's a -1, I would need 3 of them to balance out with that +3. Now, your name would just be aluminum. I do not need a Roman numeral because it is not a varying charge. It's always a +3. And it would just be simply acetate. Next one, I have Hg with a +1. Ugh, keep doing that same mistake. NO3 with a -1. So this one's easy. They're already balanced. All I got to do is just slap them together. HgNO3. Now, when it comes to the name, Hg is mercury. And if you look on your periodic table, mercury is in your transition metals. So mercury is right here. That is a transition metal. So anything in orange needs a Roman numeral. Let's go back up here. So remember, it tells me the charge, not how many I have. So mercury 1, and then NO3 is nitrate. Okay, next one, K1 plus 1 and P with a -3. This is not balanced, so that means I'm going to take the 3 here, take the 1 here. So my formula would just be K3P. K is potassium, and phosphorus becomes phosphide. Okay. Next one, I have the name aluminum nitrite. So aluminum is Al with a +3. Nitrite is NO2 with a -1. So please do not get that confused with nitrate. So make sure you underline that last few letters to kind of tell you what to do. So I'm going to see these are not balanced. I need 3 of these nitrites and only 1 of these aluminum. So I'm going to put 1 aluminum. Then I'm going to put nitrite in parentheses and then put a 3. Okay, so remember, you cannot alter nitrite. Next one, I have Ag3N. So Ag is silver. That is always a +1. And then nitrogen, N is just nitrogen, that's N with a -3. So that's why you have 3 silvers, because each one's a +1. Then for the name, I would just put silver. And then nitrogen becomes nitride. Next one, I have calcium phosphate. So calcium is a +2. Phosphate is on your list. That's PO4 with a -3. Those are not balanced. So I'm going to take the 3 to the calcium, take the 2 to the phosphate. So I need 3 calciums. And I'm going to put phosphate in parentheses first and then put a 2. And there's your balanced equation. Okay, so I'll do a few more of these and then we'll probably call it quits from there. So Rb2O, so Rb is on your periodic table. That is a +1. It's in that first group. Oxygen is a -2. So that's why there's 2 Rbs for 1 O. Rb is rubidium. And then oxygen becomes oxide. Okay. +4 and OH -1. So Pb, so I can see these are not balanced. I'm going to take the 4 here, take the 1 here. So I only need 1 Pb, but I need 4 of these hydroxides, but I'm going to put OH in parentheses first and then put a 4. Now, if you look, Pb is a transition metal, so that means we do need a Roman numeral. So my charge is a 4, so there's my Roman numeral. So this is, oh, sorry, this is not iron. Messed that up. Pb is lead. Okay, and 4 would be IV, and then OH is just hydroxide. That is on your polyatomic list. Next one, I have SN with the F2. Now, this one can be, I like this one because you're trying to figure out what is the charge of SN, because SN is actually a transition metal, meaning I do not know what the charge is. So we can find that by looking at your anion. Your anions never change. So if I have F with a -1, that is always fluorine. Okay, fluorine's always -1, and I have 2 of them. That means my total negative charge would have to be a -2, because 2 times -1 would be -2. Now, when I give you these formulas, these are balanced. So I'd see, what would SN have to be balanced out with a -2? It would have to be a +2. Now, since there's only one of these SNs to take that +2, that means that is the charge of SN, so it is a +2. Now, SN is a transition metal. That is called tin. And since it is a transition metal, I do need a Roman numeral, and my charge is a +2. So I'm going to put tin 2. Fluorine becomes fluoride. Okay, and there's your answer. Calcium sulfite. So calcium is Ca the +2. Sulfite, okay, be careful with that, is SO3 with a -2. Now, both already balanced, so I don't need to do anything. So all I got to do is put them together. So CaSO3. NaBr, so Na is sodium, so Na with a +1. Bromine is Br with a -1. Those are already balanced, so that's why we just put them together. Sodium is not a transition metal, so I do not need a Roman numeral, and bromine just becomes bromide. Now, let me see if I can find one real quick where it's actually doing more of the transition metals, finding the actual charge. Let's see, I'm not seeing one that's where you're finding more of the charge, but I can do it, so let me see. Let me do some examples on my own. So if I give you formula something like this, FeO, and I want to know what is the cation, what is the anion, and what's the name. Okay, so in this case, iron, I don't know what it is. I don't know what the charge is, so I'm going to leave it alone. I know oxygen is always a -2. So if this is a -2, iron would have to be a +2 to be balanced out. So that means that is the charge of iron. So this would be iron 2 oxide. So let me do another example, one that can be a little more tricky. Let's see if I did something like Cr2, and then I'll just stick with the O. Okay, so I know oxygen is always a -2. I don't know what chromium is because it's a transition metal. So if I know oxygen has to be a -2, this whole thing of chromium would have to equal out to a +2. Now in this case, you have 2 chromiums to share that +2 charge. So what you're going to do is you're going to take this 2 and divide it by however many you have. So 2 divided by 2, that means each chromium would be a +1. So that's your charge. So my name would be chromium 1, and oxygen becomes oxide. Now, another example I saw from one of the other sheets is like, here's a good one, is what if we have Mn2S7? Okay, so S is sulfur, it's always a -2. And I have 7 of them, so 7 times -2 would be -14. Now, I know in order to be balanced, this would have to be a +14 over here. But I have 2 manganeses to actually share that 14. So what is 14 divided by the 2 you have? That means each manganese has to be a +7 in order to make that +14 happen. So my name would be manganese 7, because that's your charge. So that's going to be VII. And then sulfur just becomes sulfide. Now, that's usually the way we see the most issues, is going backwards and finding the transition metal charges. So hopefully those examples kind of help. So please go back and rewind if you need to. If you need more help, you can always contact us. So hopefully that helped you for your next test.